Is this what we want for the planet? When we burn coal, we actually produce about enough CO2 to fill about 10 million Olympic-sized swimming pools per year. Is this the wave of the future? This is a school near Chernobyl after the explosion of the nuclear fission plant in Russia. This school will be abandoned for a couple hundred years. Is this the wave of the future? Let's paint a green screen, green energy. The question is there a scalable, worldwide green energy source or potential? We have wind, we have water, we have those types of regional or local types of green energies. But up until now, there's not been a scalable, worldwide green energy source. That's about to change. So I appreciate the opportunity to speak at climate change. The title of this presentation is Lunar Helium-3 Mining, the tip of the spear for lunar economy and the pathway for sustainable, true green energy through nuclear fusion. Our company called Lunar Helium-3 or LH3M is singularly focused on extracting helium-3 from the surface of the moon. That's all we are focused on. To bring helium-3 back to Earth for existing use cases, for nuclear fusion in the future, which will be the world's first large-scale sustainable green energy source, in addition for future quantum computing. We're going to talk about all three of these today. My background is a little eclectic, but I do point out that I first learned about helium-3 when studying planetary geology, and from there I added some other backgrounds to try to understand helium-3 on the surface of the moon, how you would deal with it from an engineering, an operational, and a mining perspective. Our agenda is fairly ambitious. Big question is, why is the United States going back to the moon, or other countries too? How do you get helium-3? What are the use cases that we mentioned earlier? It's going to be very expensive to go to the surface of the moon. What are the revenue projections for this? Does it make any sense to go there? We'll talk about some challenges and then wrap up about our company. All right, so why are we going back to the moon? The obvious reason may be for scientific research or due to the fact that we're in competition with China for the next wave of Americans or Chinese to step foot on the surface of the moon. Remember, the United States did that in the 60s and 70s with Apollo. Or are we going there to prepare for a Mars mission? These are laudable, important ideas, but they're very costly. They don't generate revenue. And with global budgets for individual countries getting worse, this may not be sustainable. There may not be a sustainable reason to be on the moon for scientific research. The good news is we believe there's a revenue generator pathway, not a cost center, a pathway in which the extraction of a resource could generate enough money to pay for itself. The only resource on the surface of the moon to do that, to bring back to Earth, is the extraction of helium-3 for Earth-based uses. So helium-3 is an isotope of helium. It's not radioactive, it's fairly stable. And the most important thing is it has critical, unique uses on the surface of the Earth. So we do have some supply of helium-3 in the globe. In the United States, it's estimated to be less than 10 kilos, in some respects, maybe down to 5 kilos. And it came from nuclear weapons production, primarily during the Cold War, with the decay of tritium, which is part of nuclear fission for weapons production. That supply, again, has dwindled. The main source of helium-3, however, naturally comes from the sun. It travels in the solar wind with helium-4. It gets captured in Earth's atmosphere, so there's basically none of it on our ground. However, on the moon, there's no atmosphere, so helium-3 has been baked into the lunar regolith for billions of years. The good news is there's a rough estimate of 1 million tons of helium-3. That's enough to power Earth-based fusion for hundreds of years. However, the concentration needs to be watched carefully because the concentration is very low. It's somewhere in the neighborhood of 1 to 15 parts per billion. This reinforces the slide I just mentioned earlier. The amount of helium-3 across the globe, and in particular in the United States, has gone down dramatically. At one point, we more than likely had about 20 kilos of helium-3 a number of years ago. And that's dropped, as I've mentioned before, probably somewhere in the neighborhood of 5 kilos or less. You can't mine it, as we mentioned, because it doesn't make it through the atmosphere, and there's no large-scale sustainable method to create helium-3 that's known. Therefore, the only true source of large volumes of helium-3 is off the surface of the moon at an estimated 1 million tons. Now, again, the helium-3 on the surface of the moon has come from the solar wind. There's a lot of ways helium-3 could be in the ground called the regolith. The most important is the first bullet point interstitial. As it comes from the sun and imparts itself into the ground on the moon, the energy of impartition is very, very minimal. Therefore, it's mostly loosely attached, we believe, to the grains at the surface, probably through forces such as van der Waals forces. There may be some helium-3 deeper down from things such as meteorite impacts, but we believe the bulk of it's close to the surface. Let's talk about present use cases of helium-3. In the left-hand column, there are potential or present use cases of helium-3. The most important is radiation detection of nuclear bombs at borders. If you look to the two columns to the right, in 2008, it was estimated that we used in the United States roughly 1 kilo of helium-3. As the supply has dwindled, the amount that could be used has gone down dramatically, as you can see in the last column. Consequently, the applications in the left-hand column can barely get any helium-3, if any at all. Therefore, radiation detection is faltering without having helium-3 as the prime way to do detection, and they're looking at substitutes now. Okay, we're now going to look at two future cases of helium-3 that will demand a much higher volume or mass of helium-3. The first is nuclear fusion. So it's great that people are driving green or electric cars or taking electric trains. There's all sorts of electric vehicles. The question is, are they green? The ultimate answer is that those vehicles are only green depending on where their electricity came from. If the electricity came from burning fossil fuels, driving an electric car is just not green. So let's ask the question or answer the question, where does the electricity come from? The present source of world's electricity, 70-80%, comes from burning the fossil fuels and then nuclear fission. In order to burn fossil fuels, which is mainly through coal, you need to get the coal out of the ground. Now, the world uses about 8.8 billion with a B, billion tons of coal per year. To reach the coal, you have to scrape off or dig up the overburden on top of the coal. Then you have to use energy to mine the coal out of the ground. A rough estimate is that we would need about 0.36 billion tons of coal just to get the coal out of the ground on top of the 8.8 billion tons of coal that are being used per year. So there's energy that is required to reach the coal and to get it out of the ground. Then you almost always have to move the coal from a mine to a plant that produces electricity. If you moved 8.8 billion tons of coal, roughly 500 kilometers, you would need about another 0.24 billion tons of coal to make the energy or electricity if you used an electric train to move that coal. I'm doing this to drive home a point about the coal. Okay, so you need coal to get coal. You roughly need about 9.4 billion tons of coal. You need to mine it, you need to transport it, and then you need to burn it to create electricity. This amount of billions of tons of coal produces significant carbon dioxide and other gases. If we focus on the CO2 alone, that's almost 40 billion tons of CO2 produced per year. That's enough to fill about 9 million Olympic-sized swimming pools. So the message here is coal takes coal to mine it, to move it, and then to burn it. This all adds up. The bottom line is a significant amount of CO2 per year going up into our atmosphere. Nuclear fission. Did anybody tell us that we'd have to store nuclear fission waste materials for 100,000 years? There is no long-term storage facility in the United States for this. It was supposed to have been built in Colorado, and it never was. Consequently, most nuclear waste is typically stored at the nuclear facilities that it came from. But I'm not sure how many people are going to be around for 100,000 years. And on top of it, I'm not sure how any containment systems such as these barrels are going to contain nuclear waste for 100,000 years. We pushed it downstream to our children's children's children. As you saw on one of our earlier slides, there was significant fallout from the explosion at Chernobyl. Where the epicenter is of Chernobyl, there's a surrounding exclusion zone that's about 30 kilometers. So about 30-kilometer circle around Chernobyl, that area is unsafe for habitation for 200 to 300 years. On top of it, because of Chernobyl, there's roughly 31 deaths that took place and at least 4, if not 5,000 cancers that are directly contributable to the explosion at Chernobyl. Good news is the future source of electricity is probably going to come from nuclear fusion, which is scalable across the globe. Fusion is a reaction in which two or more atomic nuclei combine or fuse under extreme temperatures. They release lighter particles, but most importantly, they release more energy. So when done correctly, more energy comes out than goes in, which is pretty cool. There's two major reaction types to talk about. The first reaction would be something called deuterium and tritium, and that would produce helium-4, a neutron in red, plus energy. We have coined that fusion 1.0. If you had helium-3, the reaction would be deuterium plus helium-3 produces again helium-4, and this time a proton plus energy. We've coined that fusion 2.0. The big thing about fusion in general is it cannot explode. There will be no more Chernobyls. This has been talked about for decades, but it's actually right around the corner. The first contract for energy coming off of nuclear fusion is between a company called Helion Energy and Microsoft for 2028. We believe this will scale up over the next 10 or 20 years and more than likely would be with tritium unless helium-3 can be sourced off the surface of the moon. Ultimately, we believe fusion will replace nuclear fission and fossil fuels. But the question is fusion going to be green or not? And the question about green or not is really up to this slide. This slide looks at the differences between nuclear fusion with tritium, or fusion 1.0 in the middle column, or if you had helium-3, fusion 2.0 with helium-3. There's no known way to scale tritium production that's simple. First off, you have to mine lithium out of the ground, which causes its own carbon footprint because you have to mine it out of the ground. And then through a type of nuclear fission reaction, you convert it to tritium-3 fission reaction. The waste products of nuclear fusion with tritium have to be stored for 50 to 100 years. It shoots out a neutron, which is more dangerous to humans in the reactor, require more safety regulations. However, if you had helium-3, that's scalable off the surface of the moon. There's no waste products for storage. It should cause less reactor or human damage, should be much safer. Ultimately, fusion with helium-3 is green for the reasons as discussed. Fusion with tritium is not green. Where are we at in development? In the left-hand column, you can see the left-hand box, the fusion in general, primarily at tritium, has gone through a fair amount of development. Billions of dollars have been spent by more than 10 countries on this project. With respect to extracting helium throughout the surface of the moon, in the right-hand box, it's in its infancy. And I would point out the terms in some of these slides coming up is TRL means technical readiness level. That is a term used a lot in the space industry, and it goes from a scale of 1 to 9. 1 is sort of like an idea, and 9 is completely commercially built out. So TRL 3 and 6 in the left-hand column is the middle level where it's gone beyond early testing or at that testing stage, some early development, early hardware. Over on the right-hand box, TRL 1 to 3 is a much earlier stage in development. Okay, let's look at some broad stroke numbers. If fusion was adopted across the globe to produce electricity, first off, that's about a $40 trillion valuation. Now, that's not new. That would replace nuclear fission and the burning of fossil fuels. So don't let that distract you. The most important question is if you had fusion across the globe and then you could use helium-3, how much helium-3 would you need? If you go all the way to the bottom, the take-home message is you need about 570 metric tons of helium-3 per year to power fusion across the globe. Now, that's green energy, as we discussed, but also just from a volume point of view, that's only 570 metric tons compared to just about 9 billion metric tons of coal that has to be burned if you were to use coal or fossil fuels. The next future use case is quantum computing. In this case, it's not going to be so much about massive volumes of helium-3, but quantum computing, as we will see, is a strategic thing. So fusion was more about green energy, and quantum computing's focus is going to be on speed and strategy. So quantum computing is experimental, but it's advancing rapidly. And I love this example of how fast it can be. If you took a string of numbers that was 2048 in length, and you try to break it down into its prime components, that would take a classical computer about 10,000 years. A quantum computer can do that in less than half a day. The speed is mind-boggling, and the potential applications are a lot good and some bad. We suspect you can discover some drugs with this, potentially cure some cancers, and it's going to allow for major geopolitical strategic dominance from one country to another for those that have it and those that don't. What does helium-3 have to do with this? Well, in order for these computers to function correctly, they have to be cooled down to like 0.01 Kelvin. This is not your refrigerator at home type of cooling. This is really, really cold. And without helium-3, you can't get it that cold, and they don't function that well. By the numbers, each quantum computer is roughly estimated to use about 1 to 10 liters of liquid helium-3 for cooling. No one has estimated how many quantum computers there'll be in the future, so we just took a stab at that to give you an idea. If you made a rough estimate of 10,000 quantum computers 15 years from now, if you do the math, the total amount of helium-3 that will be needed is about 4 metric tons. There are national security and strategic implications here. Again, helium-3 is essential for quantum computer cooling, or they don't function. Quantum computing or quantum dominance drives AI, encryption, and cybersecurity, and can aid in strategic defense, intelligence, and economic leadership. Without helium-3 for the United States and its allies, that could be a problem against its adversaries. We mentioned that the cost of going to the moon is extraordinary, so the revenue must offset this. Let's look at this from a projection point of view. Today's helium-3 prices are $30,000 a gram. Ironically, tritium costs more than that. That's about $30 billion a metric ton. We expect these prices are going to fluctuate up or down. They will probably go up for quantum computing, and they will probably come down for nuclear fusion. But these numbers are still staggering. If you look at fusion by itself, if 570 metric tons are multiplied, you need about this would be about $17 trillion of revenue per year. On the quantum side, 4 metric tons equates to about $119 billion of revenue. That is a fair amount of money, and we expect those to fluctuate but you're still looking at trillions of dollars of revenue per year. Okay, all that sounds great and it theoretically sounds wonderful, but let's talk about some practicalities of this. And first, let's look at competition. I think this is important because our company is not the only entity talking about extracting helium-3. China is probably the most important geographic powerhouse to talk about extracting helium-3. They brought back samples from the surface of the moon and they've announced their intent to extract it. My personal belief is this is to fuel their quantum computers more so than potentially green energy. India has also expressed an interest in extracting helium-3. Their space program is behind China and the US, but it's rapidly expanding and catching up. Unfortunately, the United States has no public position on this, which is why our company has run around the United States and done many presentations at quantum fusion, space policy, conferences, a lot of different conferences to a lot of different audiences to promote the extraction of helium-3 to get the United States to have a public opinion on this. There are private companies, including ours, that are looking at helium-3 extraction. Our company, as we will see, has taken a lunar focused approach to work with the moon's environment and not against it. What that means is we're going to use extraction techniques designed for the lunar environment, not Earth-based techniques. This is probably one of the most important slides in this presentation. In order for this to be successful, and success here would be defined in some respects as a positive return on investment eventually, three things must happen. The cost of transportation to the moon must come down proportionally, similar to what happened to placing satellites in low Earth orbit. Second is fusion must take place across the globe, and this needs to be switched over to helium-3. That's where the volume of helium-3 comes from. And third, to the bottom right in red for a reason, is you have to go to the moon using lunar-based and not Earth-based techniques, and we're going to talk about that coming up. Okay, for fun, this is a gold mine in Australia. It's an open pit mine. The mining process for gold in Australia or copper in the United States or uranium in Europe is the same no matter what, in which you have to use energy through blasting or grinding to get ore out of the ground, then put it into a processing plant and heat it or chemically treat it to extract your resource, and you dump out the back end something called tailings or wasted rock. Now that looks nothing like the moon. And this robotic mining system looks nothing like what I just showed you. This is some potential methods of extracting helium-3 off the surface of the moon that roughly some people have proposed. And in the front of this is a round thing called a bucket wheel, which requires energy to grind up the ground and transport the ground up ore through a conveyor belt inside this vehicle and heat it or chemically treat it. And then you dump out the wasted rock out the back end and you hold on to your precious resource. In this case, that would be helium-3. This again looks nothing like that mining center I showed you in the previous slide in Australia, but they're the same. The methodology is the same. There's a fair amount of energy of extraction to get the ore out of the ground, and there's a lot of moving parts. Neither one of these issues or topics we believe will work well. A fair amount of energy and a lot of moving parts, and we're going to show you why. Okay, I'm going to go over 4 challenges at a very high level very quickly, and there's a lot more challenges, but these 4 might drive home some key points. First off is the concentration of helium-3. The good news is there was an estimated 1 million tons. The bad news is it's low concentration, and that has to come into play in your mining equation. As we mentioned, there's about 1 part to 15 parts per billion of helium-3 compared to, or concentration of helium-3 compared to, for example, an Earth copper mine, which might be 0.5 parts per 100. So if you were to try to use standard Earth mining techniques, what you're basically kind of doing is using an extraction process to extract 1 part of helium-3 for every 999 million parts of unusable tailings. The energy equation for mining doesn't make any sense. We have come up with a low energy extraction process designed for lunar conditions and that concentration of helium-3. Second challenge is the dust. The regolith, which is the ground, its dust looks nothing like Earth-based dust. It's sharp and spickly, and you can see what it looks like under a microscope to the top right. Why? Because there's been no water or wind on the moon to erode or smoothen out the dust. Second, it's 45% silica. Third, it's charged from solar radiation. So if you walk on the surface or drive a vehicle, the dust gets kicked up. Third, there's a fair amount of iron related to the regolith. This all means that unlike Earth dust, this is an extremely abrasive and clingy substance. If we take a look back at a lesson learned from Gene Cernan from Apollo 17, he roughly said something like this: I think we can overcome other physiological, physical, or mechanical problems except dust. He was trying to tell us in his short time with Apollo 17 in 1972 that unless you deal with this dust, you're just not going to survive mechanically or from a human point of view on the surface successfully. A second slide driving home this dust point. Again, looking back at the last Apollo mission, which had 3 EVAs or 22 hours on the surface of the moon, which 2 astronauts were walking around. In just a short period of time, it destroyed equipment. It eroded 3 layers of Harrison Schmidt's astronaut's boot, which is about 12 to 15 layers. And it adhered to virtually everything. Take a look at that image. That's Harrison Schmidt's suit, and it's all gray. And when he got it, it was all white. So our suggestion here is this dust is so damaging. If you have a lot of moving parts, it's going to get destroyed and just not work. We've come up with a system to recognize this problem that uses the least amount of moving parts. Next, the environment of the moon is a vacuum, basically. And over the next couple slides, we're going to drive home this third and fourth point. Our mining system, as you will see in upcoming slides, takes place underneath a rover. And if you heated the ground and, for example, helium-3 comes out of the ground by doing something like that, the helium-3 is going to go shooting up at ballistic speeds. If the rover is open to the environment, this helium-3 is mostly going to go shooting off into the atmosphere. So we're trying to minimize that. And we have a skirt that goes all the way around the rover, which I will show you in a couple of slides. But I want to point out the fact that we're trying to move as many loose rocks around the rover. We don't want them underneath the rover. Now imagine mining just like a farmer. The rover is going to go up and down and up and down, and we don't want to push the rocks from its first pass over into the next lane coming up. So a regular snowplow like on Earth on a single angle would do that. We've come up with this bi-directional plow, which we believe will move many of the loose rocks around and behind the rover. Here's another slide to go over this a little bit more. If you imagine the rocks hitting a bi-directional plow, number one, it will direct the rocks as much as possible around the rover. And slot number two is where they will be captured by a railing, and then they eventually end up in area number 3, which is in red, and they'll be directed behind the rover. The goal is to, as much as possible, won't be perfect, to move as many of the loose rocks around and behind the rover. And I didn't have a slide about it, but the skirt around our rover, or the bottom of our rover actually has a skirt around it to sort of self-contain the volatile gases helium-3 as it gets heated up. So I didn't really show that well, but there is a skirt around there that's malleable or can move, and that would help contain some of the volatile gases or the helium-3 from going shooting up into the atmosphere. And that's what that plow is designed to do, is to help keep the rocks away from going underneath the skirt. Okay, Lunar Helium-3 was built a couple of years ago, or a number of years ago, with the intention of extracting only helium-3 from the surface of the moon. We started out with a blank sheet of paper and said, how can we do this from an objective point of view? And we said we need to work with the moon and not against it. That kind of concept means we're going to use, again, lunar extraction techniques and not bring up Earth-based techniques. Our team is diverse with lots of different backgrounds to try to understand the moon as much as possible. It's going to take an extremely long period of time before people understand more about the moon. This is our attempt to understand as best as we can what the lunar surface is going to do when we try to extract helium-3. As I sort of mentioned earlier, we've done significant outreach with our primary goal of getting the word out about the extraction of helium-3 to different conferences across the United States and is soon to be outside the United States to do this. We have a number of patents that are pending and issued. And here's an important slide. This is what we are focused on. If you look at the graphic at the bottom, there are 5 stages there roughly. Our company's focus is on those 5 steps, from targeting the surface and the subsurface or below the surface, heating the ground, directing vaporized gases. And by the way, it's not just helium-3 that comes out of the ground, but other things such as hydrogen and helium-4. So direct these gases so they don't go escaping into the atmosphere, separating the gases, taking the gaseous helium-3 and then compressing it into a liquid form, because liquid helium-3 is the form that helium-3 will take for transport back to Earth, because it will be a much more compressed volume. So if we sort of begin to summarize all this, there's an estimated 1 million tons, that's a rough number of helium-3. That's enough to power fusion for hundreds of years. There are existing Earth cases now, but the volume of that is low for helium-3. However, the up and coming top 2 future use cases is fusion 2.0 with helium-3 and deuterium. Worldwide, when it's fully adopted, that would be about 570 metric tons per year at a revenue stream of about $17 trillion in today's dollars. For quantum computing, if you had to cool down 10,000 quantum computers, you would roughly need about 4 metric tons, which is about $119 billion worth of revenue. The success triangle that I showed you before was the success from a revenue point of view, because ultimately it'd be nice if this was not a governmental initiative. It might be governmental private at the beginning, but ultimately it'd be nice if this very large ongoing process was private. And private companies can't just burn money, they have to actually make a revenue. So the success for that ultimately would be when transportation costs come down, infusion is adopted and switched over to helium-3. And in red again is you need to use lunar-based mining techniques. You cannot go in there like a bull in a china shop and use earth-based techniques. They won't work. Our company is singularly focused on the extraction of helium-3 and trying to understand the lunar environment. And that last bullet point we haven't talked about much, but the extraction of helium-3 is the tip of the spear for lunar economy. Now, what does that mean? That is the main driver why we would have robotic devices on the surface of the moon, rockets going back and forth, and most likely humans on the surface to do support and do repairs. There'll be a lot of infrastructure for this economy. It will require partnerships with other companies and other countries. With that, I appreciate your time today. If there's any questions, please visit us at lh3m.com.